Welcome to ECE 302. This is lecture 3.2 on probability mass functions. I am Professor Stanley Chan. Today we are looking at section 3.2 of our course. It is on the topic of probability mass functions. If you recall our discussion of the previous section on random variables, we ran through some of the most basic definitions of random variables. We also learned why do we need random variables. Today's lecture is going to discuss one extremely useful characterization of random variables, which are the probability mass functions. This probability mass function should not be a stranger to most of you. If you have ever played a data set before, you know a term called the histogram. Probability mass functions are essentially histograms, with some differences. So we are going to explain the definition of probability mass functions, and then we're going to draw the linkage with histograms. Finally, we will also talk about the properties of a probability mass function. So by the end of today's lecture, you will be able to tell somebody what is the meaning of a histogram and what is the meaning of a probability mass function. What do we mean by finite sample? What do we mean by the ideal histogram? This is a very important concept which will help you understand what we call the generative model in data analysis. So to start with, let me remind you what we have discussed in the previous lecture. We defined the random variable, and we say that a random variable is a function that translates words to numbers. If you recall this diagram, we all start with a sample space omega, where inside the sample space omega, we have many events, psi 1, psi 2, and so on. These outcomes, or if you look at the subsets, they are the events, they will be mapped to numbers on this real line. And this mapping is called X. And this is what we call the random variable. So the random variable is a mapping that maps an outcome to a number. Now, if you want to calculate the probability of certain events, then you are looking at this number, X psi equals to some number A. You need to go back to all the possible outcomes that got mapped to this number A. And so you will come up with a subset, and then the probability that X equals to A, we know from the last lecture that this is the probability of X inverse of A, where this X inverse is really the set that contains all the psi, such that X psi equals to A. But there are just too many numbers here, and there are many, many different events. And if you need to do this kind of inverse mapping every time, it could be very, very tedious. And therefore, we need to have a systematic way of describing all these events. And this comes to the notion of probability mass functions. The definition of a probability mass function is as follows. The probability mass function of a random variable X is a function which specifies the probability of obtaining a number A. So let us look at the notation, and you will understand what we mean. On the left-hand side of this notation, I'm defining a function called P, and I'm taking a number A. So it is really trying to evaluate the probability of something at this state A. And then on the right-hand side of this equation, it is the probability of x equals to a. Okay, so we're defining this function p, the small p. It is calculating the probability of this random variable that hits this state. So implicitly, what this is doing is calculating the set of all the size such that x psi equals to a. All right, so now I also want to be explicit about which random variable that I am looking at, and so I put an x on the left hand side of the small p notation. So how do we understand that? It is important to realize the difference between this x and also the a. Here, this x refers to the random variable, and this a refers to a state. So what do we get out from this probability mass function? Here is the real line where your xa is living on. So you can have multiple states. These states, they could be, they are the a's. For example, they can take the value 0, 1, 2, 3, and 4, and so on. These are all the possible states. And then if I'm drawing the y-axis as px of a, okay, and then this number at 1, I will have some value. This number will refer to px evaluated at 1, and this point would be px evaluated at 2, and so on. So what are they? They are the probability, because according to this definition here, these are the probability that x will take a state 1, and so on. Therefore, x is a random variable and a is a state. So how do you understand a random variable? You can also think that a random variable, it is random because it has many possible states. So whenever people talk about a random variable, what you can think of it as, certainly it will be a function that goes from the sample space to a number on the real line. But another easier way to think about random variable is that it is an object x. And behind this object, you can think it as it has multiple possible states. Okay, so for example, 1, 2, 3, 4, these are all the possible states that x can take. X can take 1, x can take 2, 3, or 4. The probability that x will land onto a particular state is specified by this probability. Now, if you have a deterministic number, x is a deterministic number, and then it is always giving you the value of 1, there's no other way of other possible state, then it is really just one pulse. A random variable, you can have multiple pulses. Okay, and here this number will always be 1.0. Okay, or you can think that all the probability is concentrated at 1, and so you have no other ways of getting another state. Here it will be that the sum of all these states will give you 1. So this is a random variable. This is a deterministic quantity. And therefore, a random variable is random because it has many different states. And the height of this probability mass function tells you the probability of landing on this particular state. Let me describe an example to make this more clearer. Suppose you flip the coin twice, and then you define x as the number of heads. Then the probability mass function will be px of x. And now there are two different x. One is a big X, and then here it will have a small x. Big X refers to the random variable x. This small x refers to the state. And how many x that you have, how many small x that you can have states 0, 1, or 2 for this problem because you're talking about the number of heads. Okay, so then we can calculate these three states, 0, 1, and 2, and then we evaluate the probability of this random variable x. So let's carry out the calculation. If you want to get probability of px of 0, this is the probability that x equals to 0, that will give you 1/4. Here that will give you 1/2, and here will give you 1/4. And now we can draw the diagram of 0, 1, 2, and so on. And this is the state. This is the small x. And then the y-axis, that would be the p of x. And certainly this, I'm talking about this big random variable, big x. And this is the random variable that you're talking about. This diagram, 1/4, 1/2, and 1/4 is the probability mass function of the random variable x. It has three states: state 0, state 1, state 2. The probability of happening will be specified by these numbers. So you ask, what is the random variable x? The random variable big X is this figure. This is the random variable. What are these numbers? They are the small x. Okay, x0, x1, and x2. These are the possible state of this random variable. Let me also clarify the difference between a variable and a random variable. Suppose you are solving this equation, 2x plus a equals to 0. If your a, this constant, is fixed, then x is just an ordinary variable. Okay, in the usual sense, you have an equation, you have a variable, you solve this equation, then the variable gives you a number. That is just an ordinary variable. If your a has multiple states, and this is a random number, then x is also random, and we call x as a random variable. In fact, if a has multiple states, a is also a random variable. Okay. But just to clarify the difference between an ordinary variable and a random variable, you can see that the equation that will govern the case here is that 2x plus 1 equals to 0. Okay, so I'm just putting a equals to 1 as a particular example. And here, you can have three different equations. And depending on what a that you're choosing at, you can have different solutions. All right, so is there any randomness? There is no randomness associated with this ordinary variable case. And is there any randomness here? There is randomness. It really depends on what random a that you have. And so you ask, how many states are here? There's only one state, one and only one state, because it is deterministic. You tell me the a, I tell you the x. There's one-to-one correspondence. There's nothing random here. How about this x? This x, you can actually have three possible states. Okay, depending on what values of a that you are getting at. So you can have three possible states, and then the probability of getting these states is, let's say in our example, we are assuming equal probability between +1, 0, and -1, and therefore you have equal chance of getting +1/2, 0, and -1/2. Okay, and what is the probability mass function for this case? Is literally not applicable. But if you do want to be explicit, then here you can say that this variable x can only take a mass with height of 1 at -1/2. And here I will be able to take three states at -1/2, 0, and then 1/2. And then the height would be 1/3, 1/3, and 1/3. So you can see that the difference between a variable, an ordinary variable, and a random variable is literally this PMF, or the probability mass function, where in the random variable case, this probability mass function, you will have more than one state. For a deterministic case, this random variable, this x, will only have one state, and now it becomes deterministic. So this is a difference, a most significant difference between a variable and a random variable. Now, certainly, you need to remember that a random variable is a function. That's also true. Okay, a random variable is a mapping that maps from an event to a number. That's still true. Okay, but I guess this will be an even more easier to remember diagram for you to contrast between a variable and a random variable. So with this definition in mind, let us move on and talk about something that might be familiar to you guys. This is notion of histogram. We all know what histograms are. If you go to Wikipedia, you type English letters frequency or probability, you'll be able to find a diagram like this. What are they? The x-axis of this diagram contains all the 26 alphabets from A to Z. The y-axis is the relative frequency of occurrence for each of these alphabets. For example, the vowels A, E, I, O, U, they have relatively higher frequency of happening. Consonants like a B, a G, X, or Z, they have lower chance of happening. This is what we call the histogram, because this is calculated based on a large collection of alphabets from the dictionary. So we know what histograms are. Histogram is just a bar chart that shows you the relative frequency versus all the possible categories. So we all know these. Now, the histogram here has a very, very good similarity with a probability mass function. Why is that? We call that a probability mass function has state, and then we have probability. The states are all the possible choices that you can have. So here it will be all the possible alphabets. Okay. Now, if you apply the mapping, you can map this to 1, 2, 3, all the way to 26. How about the y-axis? The y-axis, this is just px of small x. And so that will give you some impulse. And the impulse will be the probability that x equals to a small x. Okay? The probability that the random variable is hitting that particular state. And it is again a train of impulses. And that is extremely similar to a histogram. Okay? And that's why when you try to think about random variables, one very good way to think about them is to just treat them as histograms. All right. Now, what is the difference between a histogram and a probability mass function? Well, the difference is that the histogram is computed from the data set. This is computed from the random variable. Let us take a look at the following example, and you will be able to see the main difference between a histogram and the probability mass function. Suppose you throw a dice n times, and you record the relative frequency of getting 1, 2, 3, 4, 5, and 6. If you throw the dice 100 times, you will be able to get a diagram like this. Okay, the x-axis will have all the possible states, which is 1 to 6. The y-axis is the relative frequency of happening. Now, certainly, with only 100 dices, this histogram may not be consistent from one experiment to another experiment. So if you throw the dice 100 times today, you get this histogram, and then you do the experiment again tomorrow, you will get another histogram, and I promise that the two histograms will not be the same. If you do the experiment with 1,000 dices, the histogram will become slightly more flat. If you do it for 10,000 trials, it's almost flat because we're assuming that the dice is a fair dice. Now, if you do this experiment infinitely many times, you will be able to get a histogram, which you can imagine that it will become flat all the way. Now, what is that? Well, this is actually the PMF, the probability mass function of a uniformly distributed random variable from 1 to 6. Okay, so let's say you have a random variable x, which is a dice. Okay, you have 6 states, equal probability. And so what you will have is that you draw all these x, and then you're plotting px of small x. And since they're equal, you will be able to get this. Okay, so this is generated from the problem. It is generated directly from the random variable that you're studying. And the relationship between this one and then the other ones is that this is the limiting histogram, or we call them the ideal histogram, where the number of trials goes to infinity. And you can see that why this is true, because as n goes to infinity, the random fluctuation for each particular state becomes smaller and smaller. And so ultimately, the histogram will converge to the true probability mass function. So the difference between PMF and a histogram is that the histogram always comes from the data set, which is a finite collection of data points. A PMF is generated from the random variable, and implicitly what it assumes is that you have infinitely many trials. And therefore, the histogram will converge to this true PMF as n goes to infinity. Therefore, we call them PMF as the ideal histograms. So you may wonder, why should we study probability mass functions? The key difference is between this ideal histogram versus what we call the empirical histogram. Ideal histogram is the histogram of the random variable, which is the PMF. Empirical histogram is the histogram you get from the Excel spreadsheet based on a finite collection of data points. Certainly, you always want to have something that is ideal, because you don't know how many sample points you have, and you do not know how good is your sample size. And so if you know something about the true distribution, then you can quantify with only 100 samples, are we good? Or with 1,000 samples, are we good enough? Another reason why we want to study the PMF is that we want to model the data. Histogram is a non-parametric model. And what we mean is that in order to get the histogram, you need to tell me how many bins that you need. In each bin, you can have a height, and therefore, depending on the number of bins, the degrees of freedom is the number of bins. And therefore, histogram is non-parametric. There's no single parameter that can describe the histogram. Versus, if you start with a random variable, let's say you are looking at a random variable of a coin, then knowing the probability of getting a head, you will know the probability of getting a tail. So this entire experiment is specified by one parameter. And in many cases, for example, if you know something about the normal distribution or the Gaussian distribution, you know that once you know the mean and the variance, you will be able to specify the entire model. Versus a histogram, you cannot. You still need to draw all these bars in order to show you the histogram. So in terms of modeling data perspective, with a parametric family, or if you know what kind of PMF that you're studying on, you have a much better way of describing the data. So this is a summary of the data. The third reason why we want to study the probability mass function is the generative approach. The idea is that you want to synthesize data and test whether your learning algorithm is giving you what you want. Let me show you a diagram here. Suppose you have a random variable x, okay? And this random variable, of course, it has to come with a probability mass function. So you know what kind of number are being generated. And so that will give you some synthetic data set. And then based on this synthetic data set, you are going to do some kind of learning. And then you're going to make some inference. By inference, I mean then learning the underlying model parameters. And then you want to see whether your model has been chosen correctly or wrong. This data set can also be used to compare with the empirical histogram. Because if you only start with your empirical histogram, then you have a trouble of finding out what is the underlying generator. So let's say you do not know anything about the random variable, you don't even assume a model of the underlying random variable. You're only presented with a histogram, and we want you to make predictions of the future. It will be extremely difficult task because all these data points, they are allocated in a histogram. Now, certainly there are ways to do inference based on histogram, and there are many powerful non-parametric techniques. But on the other hand, if you want to verify whether your learning algorithm have done the correct job or not, with only the empirical data sets, you will not be able to verify. So what you can do in this case is that you can use the generator to generate some data. And since you know the ground truth parameter that comes out from your model, you can test whether your learning algorithm is able to faithfully give you the true model parameter. And then once you're confident that your model is working and your algorithm is working, then you can go back to the actual data set, which is a true histogram, and then you get the parameter from this data set, and then you will have a sense of how good is your model prediction. So the PMF can serve in multiple ways. It can be used to model the data. It can also be used to generate synthetic data. And these are extremely important techniques in modern data analysis. So now it goes to the third part of today's lecture. Here I will talk about some properties of a probability mass function. The basic property of a probability mass function is that if you sum over all the possible states, it has to give you 1. Now, why is this true? This is just coming from the axiom. If you have states x1, x2, and x3, x4, you sum all these numbers up. This should give you 1. Because why? Because these numbers can be mapped back to the sample space. So this number will map to a sample space here, to get back to event here. This number can map to another event here. This number may map to an event here. And then this number may map to an event there. Okay. And because you're calculating over all the possible numbers that can be mapped by this random variable x, and so when you do the inverse, it has to cover the entire sample space, and therefore when you apply the probability to this entire sample space, certainly you will get 1. Okay, and here is the proof. It's just the a mathematical description of what we have just drawn in this diagram. Let us look at an example to make this clear. Suppose you have a random variable with the following PMF, we want to calculate the constant C so that this probability mass function becomes a valid probability mass function. Now, this probability mass function has this form of 1/2 to the power k, and k will go from 1, 2, and so on to infinity. So we can draw the diagram assuming this C is 1, okay? Then you can have 1/2 when k is 1, 1/4 when k is 2, 1/8 when k is 3, and so on. So this is the trend of your PMF. And so now we want to calculate the C, okay? So how do we do that? Well, we know that if you sum over all the possible states of Px of k, now in here I'm using the Stanley variable k, so let me sum over all the possible k's, and then k will go from what? K will go from 1 all the way to infinity, and by the theorem we know that it has to sum to 1. And so what is this infinite sum? This is just 1/2 plus 1/4 plus 1/8 plus ... and then we want it equal to 1. Now don't forget that this Px, you also have a C here, and so you have a C multiplied with all these infinite sums. And so you have the C outside, and then this infinite sum is what? It's 1/2 times 1 plus 1/2 plus 1/4 plus ... plus. Okay, and then that will give you 1. And this infinite sum is 1 minus 1/2. And then certainly outside you have 1/2, and then there's a C, and that will equal to 1. And so now you can do some cancellation between this and that, and you can show that, oh, C is actually 1. Okay, so you have found the constant C. Let us try another example. In this case, your random variable x has this PMF where Px of k equals to C times sine of pi over 2 times k. Okay, and this k will go from 0, 1, 2, and so on and so forth. Okay, so we know that how to calculate this equation, because the summation of all the possible k's of C times the sine of pi over 2 times k has to give you 1. And then k will go from 0, 1, 2, all the way to infinity. And so now we can move out the C. The C has nothing to do with your summation. And then you have this sine of pi over 2 k, and it has to equal to 1. Now, how do we calculate this infinite sum? Well, this infinite sum can be calculated by just drawing out the diagram of sine of pi over 2 times k. All right, and so you see that when k is 0, you get 0. When k is 1, you have sine pi over 2, which gives you 1. And then k is 2, you get 0. K is 3, you get minus 1, and so on. And so you have 0 plus 1 plus 0 minus 1. Okay, so this is 0, 1, 2, 3. Okay, and then you just repeat this period. Okay, and then plus 0 minus 1. So this is one cycle, the other cycle, and so on. And you can see that no matter what cycle that you are at, because one cycle will give you a 0, and so all the cycles will always give you 0, and therefore you have C times 0, and that will give you 1. Wait a minute, what's going on? So does it mean that C equals to what, right? Because no matter what C that you give me, C times 0 cannot give me 1. So is there something wrong with this problem? I'm just following all the procedures that you are describing. Do you realize what the problem is with this example? Well, the problem is not with this calculation at all. This calculation is completely correct. The problem of in this example is that this Px is not a PMF. Wait a minute, how can this be possible? This is not a PMF. You have given me the equation. Well, a PMF is what? A PMF is the probability that x will equals to the state, and in this case, the state is k. And since this is the probability of an event, all these probability values has to be non-negative. Okay, but what do you have here? Here you have probability of x equals to 3, and you have -1. Now, what is this? This is violating the axiom of the probability. Okay, this cannot happen because for any event, the probability has to be positive, or at least non-negative. And therefore, there's nothing wrong with our calculation. It's just that this problem is undefined. This is a wrong problem. So this tells you that when you try to solve a problem, don't just jump right into the equations. Instead, try to look at the problem and study the problem more carefully, and perhaps draw a diagram to ask yourself whether the problem is well defined or not. So I hope that this example has given you some demonstration of how to do debugging when you are given a probability problem. And here's one of the very useful tools, which is to check whether the problem is well defined by looking at whether all the probabilities are positive or not. So we have concluded this lecture, and let me remind you what we have learned. We have learned what is a probability mass function. The probability mass function really is a histogram. It is the ideal histogram that happens when you have infinitely many samples in your data set. The probability mass function is also the characterization of a random variable. By knowing the probability mass function, I will be able to know everything about the random variable. And we also talk about some properties of the probability mass function. So if you have any question, please let us know. You can post your question on Piazza, or you can send us an email. We also encourage you to try out our homework. And if you have a question, let us know. So in the next lecture, when we come back, we will study more properties of the probability mass function. And we will study one more idea, which is called the cumulative distribution function. And we'll explain how these quantities can be useful. So thank you very much. I will see you next time.